Today I want to talk about Robert Millikan and his famous oil drop experiment, which he measured the charge of the electron for the first time about 110 years ago. The charge of the electron is one of the most important constants of the nature, along gravitational constant and speed of light. Robert Millikan was living in the United States, and Albert Einstein at the same time was living in Germany. But they had a friendship and a professional relationship about the ejection of the electron from materials because of the absorption of light. And at the end, Robert Millikan showed Einstein's theory about quantized light is more aligned with data. And his Nobel Prize is for photoelectric effect and measuring the charge of the electron. In the previous video, we talked about the measurement of the ratio of the charge to mass for the electron by Joseph Thomson. About 13 years later after that, Robert Millikan started to measure the charge of the electron, and he published the result in 1913 in the Physical Review journal under the name of Elementary Electrical Charge and Avogadro Constant. The idea of the paper was to measure the charge of the oil drop when it's moving in a fluid using the Stokes law, which is the drag force on an object moving in a fluid with the relative speed. If the charge of any oil drop is a multiplication of a fundamental charge, then Q, total charge, is equal to NE. And if we can measure Q and if we can estimate N, we can calculate E. But the challenge is to measure N because we are dealing with a lot of numbers of electrons. So how to deal with the fair number of electrons? The answer is to use X-ray, because at that time Einstein proposed the theory of the discrete electron emission using certain frequency of light. And it looks like that Millikan used this method in order to eject fair amount of the electron into the oil droplet. However, it is interesting because he disbelieved in the photoelectric theory of the Einstein and he tried to disprove it, but it looks like that he was encouraged that X-ray is ejecting fair amount of the electron into the oil droplet. Now imagine that you have several measurements of the charge of the oil droplets and your measurements are perfect, there is no mistake, there is no error, and you get something like this, a semi-Gaussian distribution that there is a maximum somewhere around 2e, and as you increase the charge of the electron, the probability and the abundance of it is going to go down, and technically the distance between those peaks are the charge of the electron. Even when your measurements are not perfect and you have some background that it is represented by a polynomial function or some function that you can see in this plot, the superposition of this signal and the background are in the way that you can still notice the discreteness of the charge of the electron. And if you can still measure the distance between two peaks, you can measure the charge of the electron. But this is not the method of the Robert Millikan, which means that he puts all the oil droplets together and measures the distance between two peaks. Indeed, he's going to measure the charge of one oil droplet several times in order to measure the charge difference for one particular oil droplets and try to find the greatest common divisor of those charges. And then you can repeat this process for each oil droplet and get a set of the charge of the electron that you obtain from finding the greatest common divisor of the charge difference. Here is the illustration of the experimental setup drawn by Robert Millikan in his paper, which I want to summarize. The experiment includes an X-ray source to ionize the air, two metal plates to apply electrical potential and create an electric field, an atomizer to spray oil droplets, and a telescope to observe the magnified droplets. The details of the experiment can be found in a paper, such as the canonical length of the telescope or the material of the oil droplets. When we spray the oil droplets, they descend due to the gravity and pass through a hole to enter a region between the plates, where the electric field can be applied to them. As they move downward, they are subjected to two forces, gravity and drag force. The drag force is described by Stokes' law, which states that the drag force is equal to the product of air viscosity, the radius of the droplets, and their relative speed. When the drag force equals the weight of the droplet, the particle reaches its terminal speed. From this terminal speed, we can determine the radius of the particle. As the radius cannot be directly observed through the telescope, this is because each particle is only a few millimeters in size, which exceeds the precision of the telescope. Instead, we measure the terminal speed, indirectly calculating the radius. Millikan applied other corrections, including buoyant force from the density difference between air and oil, and also the effect of particle radius relative to the air's mean free path. The second step is to turn on the electric field, causing the particle to accelerate upward until it reaches terminal speed, this time in the upward direction. In this case, the drag force acts downward on the particle. This process is repeated several times, allowing the particle to raise and fall multiple times while measuring the upward terminal speed each time. This is done because the particle continuously gains electrical charges. By measuring multiple upward terminal speed, we can determine the charge differences on the particle, which helps in estimating their greatest common divisor. So it would be like this. We would let it go down and measure V1, turn on the electric field and we measure V2. And then after a while, we let it fall down again and see if the V1 is independent of the charge, and then V2 prime. V2 and V2 prime are not necessarily equal. But this is not the reality. We don't see only one isolated particle. We see hundreds of particles going down. Some of them are accelerating and some of them are reaching the terminal speed. We have to pick up the proper one that we think having the terminal speed. We must remember that this experiment is subject to significant human bias and systematic errors. However, some of the statistical error bars can be reduced by increasing the amount of data collected, as more statistics improve the reliability of the results. So after we measured the upward and downward terminal speed, we can use the Newton's second law again to calculate the charge of the particle. So we can write down the force as a function of terminal speeds and other constants, and we can calculate the charge based on the electrical field that we apply. Now you can see Millikan's table that he put obsessively the time that he measured, the location he measured, and the speed he measured. And they show particle speed and the corresponding charges, which he used to estimate the number of electron n. He didn't detail his method, but there is an idea. If the charge ratio are simple fractions, especially involving primes, for example, you can identify the common unit. Again, there is no unique solution for n's, but if you calculate their ratio, you can guess them. Now if I plot the charges of the electrons obtained for each particle based on the Millikan's data, the distribution typically shows a peak at certain value, representing the most probable charge. The spread of the distribution, or standard deviation, indicates the uncertainty in the measurements. Millikan used the electrostatic unit to report the charge because it was the standard in centimeter, gram, and second. A significant portion of Millikan's paper focuses on addressing systematic errors in his measurements. An essential aspect of experimental physics is that the methodology should not influence the results. For instance, he discusses the uncertainty in measuring air viscosity, citing who measured it, when it was measured, and the associated error margins. On another side of the paper, he examines error arising from reading the time using the timer. And at the end, he discussed that if we are adding up all the error bars together, there would be a few percent and doesn't change the final outcome. Millikan reported the charge of the electron equal to 4.774 times 10 to the power of minus 10 electrostatic unit. But in the standard unit, it is 1.6 times 10 to the power of minus 19 coulomb. And then he uses Faraday constant and the measured charge of the electron to estimate the Avogadro number. Avogadro's constant is a number of entities in a mole, and Faraday constant is the charge of 1 mole of electron. And it was measured at the end of 19th century by the electrolysis of silver. Avogadro's constant is 6.6 times 10 to the power of 23. It's a huge number. That was not the first time that we had an estimation for Avogadro's constant, but it was the first time we measured the charge of the electron. It is an incredible number like the speed of light or pi, and Robert Millikan was the first person who had the privilege to discover that.